All right, we're live. Okay, my name is Jeremy Seek. I'm sort of the original primary author of the Boost Graph Library, among other things. I have to thank Doug Greger, who was up here earlier, for sort of prodding me and bringing me out of retirement to come and talk with you guys today. I'm a professor down at CU Boulder. Midway through the tenure process, I think you guys have heard what that's like. And what else? What have I been doing since the graph library stuff? I was very much involved with the concepts language feature extension. My PhD thesis was very much sort of all about sort of setting the groundwork for the concepts proposal. What's that? Rooms. Am I in the wrong room?
No, you're probably in the right room.
Is this food?
I'm just.
Are you?
I don't know. That's what I'm wondering. Is if the other hall is packed. Let me go over and check.
Okay.
And see.
Okay. Well, we'll figure out what's going on here. Yeah. So with the looking into the whole concepts proposal, my interests right now are sort of more on the programming language and language design side of things. Though my overarching goal is to make programming languages better for libraries and better for domain-specific languages and things like that. So that's sort of like long-term research. But let's talk about enough about me. Sort of the next hour and a half? Yeah. I basically want to do an introduction to generic programming. You can't really understand the graph library if you don't have a good basis in generic programming. And do a little bit of just a discussion of, the design of the Boost Graph Library. Why does it look the way it looks? And please stop me and ask questions at any time. In some sense, some of the main points I want to get across here is the rationale, the why behind a lot of the design decisions. And I don't claim they were all perfectly correct. I mean, we can now, with a little bit of time on our hands, we can look back and say, oh, well, maybe I would have done it differently now in hindsight. Or maybe, oh, no, this one really does make sense. But the reasons might not be obvious to everybody. And then maybe I'll be able to chime in and say, hey, this was the reason, and give sort of a good, cogent explanation for that. And maybe part of the reason why this is particularly important is that the Boost Graph Library doesn't look like a lot of other libraries out there. I mean, maybe now it's starting to look. There's compared to other Boost libraries, there's a lot of similarity, right? And a lot of the Boost libraries also are trying to support generic programming. But if you looking at some of the older, more object-oriented style libraries, or even some of the modern libraries today in other languages like Java, there will be quite a bit of a difference. And you might be wondering, why is it different? Why is it kind of this very strange look to it? So maybe I can help answer some of those questions as well. And then we're also going to look a little bit at using the Boost Graph Library to solve some problems. So that'll be a little bit more of a hands-on, well, not exactly hands-on, but more of like, okay, if you're coming from the perspective of wanting to use the Boost Graph Library, maybe that part will be of interest to you. And again, please stop me at any time to ask questions. I think I have about 60 slides.
Okay.
Well, thank you all for being flexible and switching over here. This is nice and cozy over here. So that's good. So where does generic programming come from, and what is it? So generic programming, I'm going to stress that it's a methodology for developing software libraries. You'll often hear the term generics, generic programming, kind of get mixed up with things like language features, like templates or what's called generics in Java or particular language features. And sometimes I think people sort of get the methodology and the language feature sort of mixed up. There's sort of two different things. You can do generic programming, the methodology, whether or not there's generics in the language, maybe harder. In some sense, C++ only has partial support, I would say, for doing generic programming right now, which does make it harder. And other languages actually have better support for doing generic programming. But really, what I'm going to be talking about mainly is the methodology and then in places where that sort of ties into particular language features. So the big idea, and this is the idea that Stepanov had when he got sick. That you can read about it in one of those interviews. I think it was a stomach flu or something. That when you're trying to implement algorithms, you really want to make minimal assumptions about the data structures that you're working on. Okay? And it's sort of no surprise that Stepanov was a mathematician, because mathematicians have been doing this for a long time. Well, they're not quite so much concerned with what we think of as algorithms, but the theorems in mathematics, in some sense, are very similar in structure to what we think about as algorithms. And you want your theorems to be reusable. Okay, and to do that, you decouple your theorems from the particular things that they're about, and instead you build these new abstractions that the theorems can talk about. And that's what Stepanov was saying. Hey, we need to use that same idea. We need to decouple our algorithms from the things that they're about. In computer science, our algorithms are about work over data structures. Okay, and so the idea here was that he's going to insert this abstraction, the iterator abstraction, in between. Okay. Now this isn't the only abstraction, and in fact we'll see more examples of abstractions today than just iterators. But the key idea here is that you want to isolate sort of what are the minimal things that the algorithm needs to know about, and then turn those into abstractions. And then that's going to allow you to use the same algorithm with lots of different data structures and make it much more reusable. Okay, and of course the standard template library is the sort of primary example of this style of programming. So just a little bit of contrast, kind of let's go back in time and think about how libraries were built, and actually still are built in a lot of places using sort of object-oriented style design. It'd be very common to see some classes like a vector or a list class, these container classes, and you just got like a giant list of functions as methods in these classes, right? So you might have merge and reverse and sort as methods of a class. And when you do it this way, let's say we have like M algorithms that we care about. Suppose we have N data structures, right? So vector, list, maybe singly linked, doubly linked, you've got your hash tables, you've got your red-black trees, all that good stuff. When you think about the amount of code that you have to write to implement all this stuff, it's M times N, right? It's a huge amount of code to support all that functionality. And so how can we, in some sense, generic programming is all about sort of reducing this code, to something more manageable. So with the generic programming approach, we don't try to put the algorithms as methods. Instead, we try to pull them out as these separate, highly reusable algorithms that can be used with multiple different kinds of container classes. And as you can as what's hinted at in the names of these template parameters here is that they're going to be implemented in terms of iterators, and then each of these container classes exports iterators. And now you can plug and play, right? You can use vector with merge, you can use list with reverse, and you just plug and play and you get your M times N functionality, but with only M plus N code. So that's a sort of a drastic reduction in the amount of code you need to write. So that's fantastic. Leaves much more time for hiking here in Aspen. So I've been up here since Friday, and we tried to go to the Maroon Bells, which is just an absolutely gorgeous mountain up there, but the road is closed for this. It doesn't open until the end of May, so you can't get all that close to it without. Though if you have a bicycle or rent a bicycle, that's definitely the way to go, because then it's a beautiful bike ride up the Maroon Creek road there. All right. So far we've sort of seen the benefits of sort of writing reusable code in generic programming, and that's in some sense that's the primary benefit that you're looking for with generic programming. But the other sort of main sort of goal that we have when we're doing generic programming is efficiency, and this might come as sort of a surprise to a lot of people. Like, there's sort of this common perception that abstraction and efficiency sort of like conflict with one another, that there's some sort of deep-seated conflict and there's no way to get both. And in some sense, history has sort of supported that claim. In many of the places where you see lots of abstraction being used, you also see low performance. And so it was actually pretty radical when the standard template library came out and people started doing performance tests with it, and they're like, whoa, this is pretty fast. I'm not going to claim that in every possible situation the STL is as fast as you could be in terms of hand-coded, but there's an awful lot of situations where it's either just as good or within a few percentage points. And that's despite having tons of abstraction going on here. Okay, and so why is it that we're all of a sudden we're somehow resolved this conflict between abstraction and performance? And a lot of it has to do with the C++ language design and the way templates work. So here's perhaps the simplest little generic function you could think of, the min function. And what happens when you call the min function with 1, 2? The compiler produces the code on the right here, instantiates it with the particular types, and it then does optimizations with these particular types in mind. It may inline things. Here it's doing integer-specific operations, so there's no runtime overhead for having all of this abstraction. So that's sort of the key. You have in some sense, the abstraction is there at compile time. It's there from sort of a design perspective, but it's not there at the runtime. Now, there's, whenever you never get anything for free, right? And so what's the cost of this, right? Well, here's the cost. And you probably all know this really well. We have some pretty long compile times in C++, okay? And that is the cost of our high efficiency. There's no way around it. There's no way to get super low compile times and and highly efficient code. That's just sort of that's reality. That's where that is where the rubber meets the road. But at least we've gotten rid of that old sort of idea that as soon as you had abstraction, you were sort of in trouble and we're going to have inefficient code. One thing I should mention is that, so this is me sort of talking from a programming language design perspective. It's sort of sad that C++ always compiles this way, in some sense. Like, you always get full instantiation. You always pay sort of the long compile time. And one of the areas of research that people are looking at, including myself, is sort of how can you sort of pick and choose when you want the long compile time versus when you want fast compile time, but are willing to let the runtime performance go slow. Like, let's say you're in development mode, maybe you don't care about your runtime performance when you're in development mode, but you want fast compile times, and so you'd like to be able to flip a flag or something to say, compile me fast instead. So that's something that I'm looking
And
at.
so what would that look like? Do you use implicit conversions or something like that? Do I already have an instantiation that can implicitly
A lot of it.
convert
So
or what?
So this may or may not be feasible in C++ as is, but a lot of it has to do with things like, we have this notion of like vtables for allowing sort of runtime dispatching for OO stuff. You could use things like vtables for things that for concepts and template kinds of things. So you basically turn compile time dispatching into sort of link time dispatching.
There is another potential runtime cost of templates, and this is one of the things that I've heard many times sort of thrown at templates, which is if you're instantiating a particular template function or whatever for types which are the same size and have the same behavior, you get multiple instantiations even though the actual underlying generated code is identical. And that then can destroy your iCache, especially if you want to type,
Right.
type loop.
Yeah, no, that's very true. That's a very good point. Right, and there's techniques you can use from a library level or an application level to fix that, right? there's just sort of idioms that you can follow to deal with that. And there are compiler techniques for doing that. I don't know whether any of that's in practice. I don't know. Do you know of any, Michael?
I'm trying to think.
I know that, like, for example, C#, the CLR compilers do it for C# as part of the JITting process. So I don't know what the state of the art is there.
Metroworks library way back when Howard Hinton did it. If like it was int or a pointer and they were the same size and they don't have constructors, they were actually running the same code.
And they did it in the library.
In the library.
Yeah, that's right. So it's the idioms that you just make sure to map it down to the same. Right. And you just use some of these type erasure tricks to do that. And this kind of gets back to what I said about, in most situations you can get really close performance-wise. I mean, these, when you're talking about iCache misses and stuff like that, now you're starting to get into the corner case kind of situations. So one of the key sort of issues when you're dealing with templates in generic programming is what types are you allowed to use when you're invoking a generic function. Okay, so here I'm calling the sort function of the standard template library with a vector, and then here I'm calling it with a linked list. Right? And we end up with an error message. It's somewhere deep inside stl:algo.h, right, the header file, and it's saying there's no match for operator minus or subtraction. Where somewhere down there they were trying to subtract last minus first, and right. So what's going on here is that sort wasn't meant to be used with the linked list class, right? So let's kind of look at that a little bit more deeply. We need to understand what these type requirements are all about. So kind of the lingo we use nowadays is that the requirements on a template are expressed in terms of what we call concepts. From 30,000 feet, you can think of these as interfaces or abstract base classes. That's at 30,000 feet. Once you look closer, there are huge differences, but it's sort of the same goal here. So a concept expresses requirements, and when a particular type, like let's say a vector, satisfies the requirements of a concept, we say that that type models the concept. Okay. So the term models is sort of the traditional name that we've used in sort of in our programming literature. Nowadays, you've probably heard the term concept map used quite a bit, because that's the keyword that we came up with that didn't conflict with as much existing code. We wanted to use models, but it just conflicted with too much existing code, so we went searching for a new keyword, which was concept map. But in some sense, maybe the better sort of just from an English language standpoint, you should think to yourself, implements is probably the best sort of word to keep in your head. So you can think of it as a type implementing a concept. Okay. So for the sort, for the good old sort function in the standard template library, it takes two iterators, and it says, and if you go look up like on the SGI STL website, you'll see these requirements on the types, and it'll say iter is a model of random access iterator. And it'll also say iter's value type is a model of less than comparable. How many people have sort of spent a fair amount of time with the SGI STL website sort of open and looking? Okay, good. So almost everybody, maybe 2/3. The other 1/3 don't feel bad if you haven't looked at it or whatnot. I'm happy to sort of talk about that. One thing that's kind of interesting here is this thing. So this iter is a model of random access iterator. That's a kind of a type constraint that you might see in a lot of other languages. Like in Java, you'd see like you can have type parameters and you could put a bound or a constraint saying that iter like implements random access iterator, right? But what about this one? This one's actually pretty interesting and unique. There's really only a couple languages out there in existence that have anything like this at all. Okay? And what's interesting is that we're not putting a constraint on iter itself. there's this relationship between iter and something called its value type. And we don't even know what that type is necessarily in this context. We just know that every iter has one. It has a value type. We call that an associated type. And then once we can sort of talk about this associated type, we can then put constraints on it and say that it's less than comparable, right? We're trying to sort these things. We need to be able to compare them. Yes, Dean.
But the value type is the existence of a value type in the iter would have to be part of the iterator model, the iterator concept.
That's right. Right, in fact, it's part of this one right here, the random access iterator concept. It's not directly, it's sort of like inherited up from the, you know, and we'll see the way the inheritance works in a second among the concepts. But you're absolutely right. And in some sense, it's sort of good that we put this requirement first, like from a reader standpoint, because you know that, oh, this thing's a random access iterator. And if you really know what this means, then you'll then be able to read the next line and be like, okay, that makes perfect sense. Okay. Yeah, good. Good thing to point out. So let's look a little bit more closely at this random access iterator concept. This is basically what it would look like in, you know, at the SGI. I've sort of pulled a chunk of the SGI documentation out. Or another good reference that's sort of equivalent is Matt Ostern's book on generic programming in the STL. There's sort of no accident that this talk is called generic programming in the BGL. Sort of, it's kind of the same idea. So what is a random access iterator? It's an iterator that provides increment and decrement, just like a bidirectional iterator. And it also can move forward and backward an arbitrary number of steps in constant time. Okay, that in constant time is crucial, right? Because you can, if you just had a bidirectional iterator, you could move arbitrary sized steps, but it takes you linear time to do it, right? You have to run a loop that gets you from here to there, as they say in Maine.
I shortly had an argument with a colleague because we were discussing the double and the queue. It has it has random access iterator, but it organizes data in chunks. And he said like, just imagine you have 1 million integers, for example, and one page can save 1,000 integers. So to grab the integer, let's say 500,000 integer, you have to move around 500 pages. So we still have linear time, but it is more short. It mostly depends on how you implement the double and the queue. But how is it?
Yeah, so this is a fantastic question, and it's when you're implementing a concrete data structure, like you're doubling into the queue, you know, and you're gonna go and make claims as the implementer of that. You're gonna make these claims like this thing is an implementation of forward iterator or bidirectional iterator, and then you have to make a choice. You know, should I be claiming that this thing is a random access iterator? And you really, this isn't so much as a choice as sort of a mathematical statement. It either is or is not, right? So, can you provide constant time access? And you already sort of gave us the answer. The answer is no.
But STL says that double and queue has random access iterator.
Then that may have been a mistake.
On the other hand, from a pragmatic point of view, if by declaring yourself to be a random access iterator you get better performance than declaring yourself to be a bidirectional iterator, a lot of people are going to screw the mathematics interpretation, aren't they?
Okay. So that's an interesting. I haven't quite heard it that way before. That what if you just happen to get better performance when you use the algorithms? Because what happens internally is you're gonna get different dispatching to different algorithms depending on what you claim to be.
Yeah.
Right. And so actually, I haven't seen examples of that. But if you in fact have some, I'd be interested to hear about that. Where by line you get it to dispatch to the right thing. The problem is though that. So I mean, maybe I should back up. So back up and explain sort of like why in the first place is it generally a good idea not to lie. Okay. And And the reason behind that is that when someone's writing an algorithm, and they then publish like how long the algorithm takes, they're going to say like, okay, this algorithm is like linear in the size of the number of edges and vertices, for example. They're going to do that computation based on assumptions about the iterator operations, right? And if you lie about the iterator operations, then sort of the big O, estimate on the overall algorithm is going to be out the door. Okay. So, and I guess maybe in some sense, the other thing is that so that's sort of the main sort of reason why we have these sort of constraints, is so that the algorithms, when you go and look at their overall time complexity, that makes sense. The other thing that they do is the dispatching, right? And if the algorithm writer is making certain assumptions and he's doing computations about, okay, asymptotically, I think this is what's going to happen. If you're constant time versus if you're not, then I want to switch to something else. So he's got a certain set of assumptions that he's working off of, and so if you sort of lie to him about that, then you basically have no idea what's going to happen but it sounds like if you just go and test it, then maybe you know what's going to happen with that particular instance of the STL, but if you go use a different version, then you may get who knows what.
maybe so. I mean, the case in point is probably one where the arbitrary size steps, for instance, is order log n or something, where so you can if you've only got a choice between random access or bidirectional, then possibly. But as you say, on most of the STL, the algorithms are pretty transparent. When we get into BGL, there may be a lot more going on, where it's harder to make that analysis.
Even in the STL, I mean, if you ever look at the sort implementations, Dave Musser's intro sort,
Yes.
that is one sophisticated piece of software. Whew. I mean, that's pretty amazing stuff. But yeah, I mean, a lot of them, you're right, are more transparent than that. So I think
I wanted to say, you say you make assumptions about constant time, but the concept cannot check that.
that's right.
And so
No, that's
you
why it's
said
up to.
part of the concept, but
It's
not
it is.
the checkable part.
Well, it's checkable by you, by the guy that's making the claim, right? I mean, this is where it all comes down to at the end of the day, right? So when you ship your double-ended queue for other people to use, and you've written down stuff about it, it's up to you for those things to be true, right? I mean, you're absolutely right that we can't automatically test it. I wish we could. I actually know over the last 5-10 years, I've sort of learned a lot about theorem proving and checking logical statements of these sorts, and it's sort of a sad sort of truth about the universe, but automatically checking sort of this kind of stuff is not just past the state of the art, but it's sort of like impossible. You know how like the halting problem is undecidable. You may have heard about that issue. It's impossible to write an algorithm that decides whether an arbitrary program will halt or not, in general. And it's the same kind of limitations that we run into in terms of trying to check to see if you really implement a concept or not.
So, I just wanted to sort of flip it down a little bit then. On the previous slide, you were saying sort required to access iterators. But actually, from a programmer's point of view, sometimes you want to be okay. Sometimes you want to say, well, it's okay if I give you 2 bidirectional iterators because I know this list is short, right? And if you're just hacking something up, or even more, I think this goes even closer to the heart of the sort routine in general. Ideally you would say sort, and you could get quick sort if you get bidirectional iterators, and you might get merge sort if the iterators come from a list. So I think potentially there's possibility for another level of interaction.
Absolutely, and that was totally, in some sense, not ruled out by what Stepanov did in the standard template library. I would think that he viewed the standard template library as this sort of low-level, fairly low-level interface that was meant sort of for like advanced programmers in some sense. And I mean, what you're saying is definitely compatible with that idea that you really want another layer on top of it, which then sort of does more dispatching and is maybe easier to use for programmers that either don't want to have to make those decisions themselves, or just they're, we're all in a rush anyway, so why not, if it's sort of, if there's automated ways of deciding what's the right algorithm, why not just do it?
Exactly. I mean,
So,
it's like, in generic programming, the book,
mhm,
where you say, I want a data structure that has these characteristics, right?
mhm,
And you get it.
mhm.
It's sort of what I'm getting.
Yeah, no, and I think, I would maybe say, go for it. Go do it. Like, go build that layer on top. In some sense, just like with last year's keynote, Andre Alexandru was like saying, oh, down with iterators, right? But really what he's saying is that we want this layer on top. It's easier to use and whatnot. And I think, we need them both for the algorithms and for the data structures. So I would say yes. It's meant to be built on. And I think Stepanov is actually slightly disappointed that there aren't, there's a fair number of people building stuff on top of it, but he wishes there were more. You know what I mean? Like, he wishes there were more levels and layers and other libraries that are like the STL. So,
But you say build on top of it, but
Mhm.
why can't it be that interface be the abstraction? For example, instead of, so you relax the requirement, so you just say iter should be an iterator. And then inside sort, you
Well,
dispatch to the correct sort.
now this just gets into sort of backwards compatibility issues and cultural issues. And if you want to create another namespace called my easy to use STL, and then have something called sort,
Right.
that's totally cool,
Okay.
right? It's just that this name std sort is sort of, for backwards compatibility reasons, we
Alright.
really can't change it.
I think what it means is if you have two kinds of iterators and you use the standard sort, but you implement a new standard library and you use sort, and one iterator random access dispatches to this underlying sort, and another
Yeah, no,
dispatches to but it's not on top of it, it's below it.
I know. Well, no, what it's doing is it's taking this lower level thing and modifying it by lifting it up. And that, if you could do that in a backwards compatible way, then
Yeah,
that might be a good way to do it. But I'm just saying that we have this backwards compatibility thing going on where that may or may not be. And so that's a whole different discussion about, things that aren't necessarily technical choices.
But that's
So
also a problem for generic code. If you do that kind of stuff, you want to dispatch the same generic code to different stuff. If you rename sort with 3 different names, you can't do that with generic code. To write another layer on top of sort, which is generic and takes 2 iterators, you have like 3 versions of them, one for one dispatch, one for another dispatch.
This is purely a naming thing, though, because what you're really saying is the same as me. Put a layer on top, but then change the name of the thing on top to be the same as the.
You
Yeah,
can't
so-
do this with iterators because the iterators don't have a reference to the original container anyway, so. it's-
You're right.
But I was going to point out something on the next slide, which is you were asking about this line problem with the STL, where you lie about the different iterator categories. There's actually a pretty interesting example of this in the Boost iterator library, which is, Dave defines a bunch of.
I wrote that too.
Sorry. I don't remember all of these names, so if I exclude I'm sorry. So you define all of these categories, and you actually separate the traversal from the access, right? And that's fantastic. The problem is that the standard libraries as they are right now, if you define Boost random access traversal iterator, which does not return non-reference value types.
We're actually going to talk about this issue a little bit.
And I was going
In
to
a
say
few
in
slides.
your slide actually over there, to be a true random access iterator, that should actually say convertible to value type reference.
Yeah. Or. No. No. This is a really tricky. I've dealt with so many standard bug. We had bugs in the standard. I think this is right actually,
Okay.
but it's it's sort of been controversial. But you're definitely right that there are lots of situations, like just in the plain old dereference, it's gonna have to be a reference return type, but you're absolutely right about that. I think these guys, that's right, but it's just a big mess, actually.
So basically what ends up happening is, and I just want to point this out, if you guys do this, if you need a random access iterator that returns anything but a reference type using boost iterators, just say it's an STD random access iterator, because several of the standard
Yeah,
libraries
these-
I've worked with will not dispatch correctly.
Yeah, well, there's a big mess there, and that's why we sort of wanted to fix up the concepts there, so.
I'm wondering if we could just focus and continue on, or is it? otherwise
Yeah,
we're
yeah,
gonna get to
let's
the-
cut
questions
this
to
off.
the end, because
Yeah.
I really want to see
Get
the
to
practical,
to the boost stuff, the graph stuff, yeah. All right, so in general, concepts can include, these are the kind of requirements that you can have in a concept. Valid expressions, these say what kind of operations you want to require. Associated types, this is where you sort of declare that iterator has a value type or a difference type. You can use refinements, this is where the inheritance comes in. You can say, like, bidirectional iterator is a forward iterator, and sort of pull in all those requirements. The efficiency guarantees for the operations, like plus plus is constant time, dereference is constant time. And then the semantic requirements, things like pre and post conditions or invariants. And like as someone else said, some of these can be sort of checked. You know, I wrote the concept check library, which kind of helps you sort of instrument the code to get error messages for this. It's not the 100% solution. The concepts language feature would have given us a much better solution. But then there's these things down here that you just have to sort of check yourself and make sure that you're being truthful about that. Okay, so just looking this example again, we can now sort of make more sense of this. We have a vector. It has an iterator associated type, which indeed is a model of random access iterator, so it's perfectly okay to use sort here. Down here, where we're trying to use a list, that's wrong. The list iterator is not a model of random access iterator, and indeed you do get an error message. It would be nice if the compiler gave us an error message that says, hey, you're not a random access iterator. That's what the concept proposal would have done. So, question?
I have a remark to the last slide.
Uh-huh.
You're saying you have to check the semantical requirements yourself.
Mm-hmm.
But this is really the hard stuff, and I think this is the core of the properties and characteristics of the concept.
Mm-hmm.
And I'm going to give a talk that is saying you can check it, you cannot prove it, but you can check it
By testing.
by testing.
Absolutely.
You can support automatic testing on this.
Yeah, that's great
It's not a
stuff.
proof, but you can do it very smart so that you can be very confident that there is
Yeah, and I
only
would-
a little
I would
probability
totally
left.
encourage people to use that
Yeah.
stuff, and to its full extent. And I believe very highly in testing, in terms of trying to make sure that you're satisfying these kind of things. And you want to, even if you were going to go and do the proof yourself, you'd still want to start with testing, because it's a lot easier to find bugs by doing tests than by doing proofs. So
The
test.
best way would be to prove it with a theorem checker, but
Yep.
for a language like C++, this is immensely complex.
Yep.
So nobody came up with a tool.
Right.
Yeah.
It's well beyond the state of the art right now. I've been tracking the state of the art pretty carefully, and we're there's some hope actually. Just recently, some results, but we have a long way to go. So, but moving forward, this is what the iterator hierarchy looks like, in sort of the current standard C++. As pointed out by Tom. This and in a lot of papers that I've written, this isn't the ideal breakdown, and it's got problems. But maybe this is the point of to ask the question: where do concepts come from? When does someone decide to create a new concept, and why? What's the appropriate time? Does someone just sort of sit there in their room and just sort of concepts pop up? You know, where do they come from? Does anyone know where they come from?
Empty space mostly.
What's that?
They come from outer space.
Outer space. Alex Stepanov.
It's the one tangible product of SETI.
SETI, yeah.
Yeah.
In my experience, they come from the experience that you discover in real-world programming the same problem more than once, and then you begin thinking, what is the common ground of this?
Amen. Amen. And just to be very specific, so you're out there programming. You're programming algorithms. Okay, so the concepts come from algorithms. Okay, it's not the other way around. And I emphasize this because in object-oriented programming, I think there was a really strong push that you sort of design this beautiful hierarchy,
Right.
and then you go and write code. And that's not the right way to do it. Okay, this hierarchy did not pop out of nowhere from outer space. No, what happened was Stepanov was writing hundreds of algorithms and variations on algorithms, and he was looking for commonality. And think of yourself more of a biologist, okay, than a computer scientist. He found these things by looking at algorithms, okay? And so if you're implementing new algorithms, don't be surprised if concepts pop up. And don't feel bashful about creating concepts, okay, if you're building new algorithms, okay? So that's where they come from. The whole point of an algorithm is to help you describe the minimal requirements that a particular algorithm needs, okay? And I would furthermore say that a concept deserves to exist if there's one algorithm that needs it.
Oh.
Because I was
going to ask the question, how many do you need?
You just need one.
Okay.
One generic algorithm that needs a concept, and boom, there it is. I mean, in some sense, concepts themselves aren't actually necessary. You could go totally a la carte, and you could say, for this algorithm, I just have this giant laundry list of requirements. But we don't do that, because it just turns out that a lot of algorithms happen to have the same requirements over and over again, and we put names on those things, right? But that also explains why there's this sort of fine-grained slicing, okay? You know, why don't we just have this one iterator thing called the be-all, end-all random access iterator, right? Well, because this guy would be the wrong requirement for an awful lot of algorithms. It would be too restrictive, and it would limit the reusability of an algorithm, okay? So like, let's say you said your find function had to have a random access iterator. All of a sudden now find doesn't work with, or it's not supposed to work now with lists, even though it really should, right? So that's where they come from. I think in some sense I already answered this. Is it better to use few or many requirements in a template? The answer is few. The fewest possible that you can get away with and still get the algorithm to work. That's an important process of trying to reduce and minimize the requirements. I mean, when is it time to define a new concept? When you're implementing new algorithms and there just doesn't happen to be a concept out there already that matches the minimal requirements that you need. So, any other questions about that? I don't know if this is old hat for some of you, but I don't think it's published in that many places, so I think it's important to kind of stress, you know, where these things come from and when to create new ones. You can actually get into problems if you try to take let's say you sort of just grab one of the existing guys, even though it's not a good fit, you can actually sort of screw up your algorithm a little bit because it might not be the minimal thing you need.
So would concepts apply also in when you're building structural, when you're actually designing
Data
systems?
structures?
Yeah, not really data structures, more like interaction between modules. So if you're working at the higher level, for example, if you're actually making a web service, would concepts in this sense apply?
Yeah, it would apply in the sense that you have algorithms in your web services or something, and if you have algorithms that kind of end up showing up in different disguises in multiple places and you want to somehow create a generic algorithm that sort of spans all of those, then that's where a concept would pop up. Okay. But it would be based on the code. It's always, you're staring at code, you're seeing commonality, and you want to pull that commonality out. I think actually this was for.
I was going to say that you also have semantic correctness with your invariants and pre and post conditions that you, for a web surface, for example.
Yeah, it can oftentimes help you express your invariance by organizing it in this way.
In my experience is it is sometimes better to recognize that a concept is already there or is identical to a concept that is already there than to come up with a new concept. For example, I did this library of interval containers, and I thought this is some new thing, but the point where I saw that such a container is just a set, it has all the properties of a simple set of elements, although it's differently implemented. This was a great breakthrough and made everything more simple. Or if you have, I don't know, in networking some grids, and you discover it can be done with graphs. I think this step is much more important than coming up with new concepts.
Well, yeah, so I think what you're saying is compatible with what I'm saying, but just in some sense maybe I skipped over what you're saying now, was that in some sense, if there's something that does match what you want, and maybe finding a match takes a little bit or a lot of thought, that's great. And you certainly want to stick with, you don't want to just come up with new interfaces for no reason. I mean, especially because when you do that, you're sort of forcing other data structure implementers to do a lot of work, right? So if there's something that fits that's already there, by God, use that. Don't make the rest of us miserable dealing with your own idiosyncrasies, right? Okay, but on the other side of the coin, though, if you really do have some fundamental different things, and you've tried hard to look at the existing things and it's just not there, then at that point, feel okay to go ahead and create a new concept.
So is there one place?
What do you mean by?
We've said several times now, if there's a concept already there, where's there?
Where's there? It's spread out. So it's, the standard library, Boost libraries, that's the main places, but there are other libraries out there as well. I guess in some sense it would be nice if we had a more centralized thing just for the concept aspect of it. That'd be nice.
Concept publishing repository or something.
Right, because these things really they're like standards. Okay, these are things that lots of people have to agree on, because this is the communication mechanism between the data structures and the algorithms. Right? And so these are things that really a lot of people have to agree on. So
I generally start with the assumption I'm not doing anything that somebody else hasn't already thought about. And I'd much rather find something that somebody else thought about.
And I'd say that's usually true.
It's
9
not
times
always
out of
easy
10.
to do.
Yeah.
And what happens is 2 years down the road you find out, oh, well, there's a much better implementation and mine isn't really what I should have.
Right.
I hate to be spoiled but cool.
You really want to get to the graph stuff.
Yeah.
I'm sorry. I'm sorry.
2/3 of the way through it,
Oh, we're 2/3 of the way through. Okay. Associated types. How many people know about traits? Good. Okay, let's skip that. Okay, so this is the end of the generic programming recap. Maybe I'll just go ahead and dive into the graphs at this point. All right, and maybe we can go a little bit late too, since we had the whole switch over and stuff. We have like a 2-hour lunch break, so maybe going a little late would be fine. All right, so graphs, right? This is it's a mathematical abstraction that we use to solve certain kinds of problems. Examples include internet packet routing, telephone network design. AT&T put a lot of the fundamental graph theory comes from AT&T Labs or Bell Labs, the older. Molecular biology, building software systems. So what we have here in a graph is you've got vertices, or also called nodes, and then edges. Right. So here's a simple graph that's describing how long it takes to drive from one city to the next in Colorado. Or not necessarily city. Mary Jane is just my favorite place to ski. And then you don't necessarily have to have things on the edges or labels, but here I'm labeling the edges with the time. And just some of the ways that we can store and represent graphs that are out there. There's edge list data structure, or this is sort of a typical edge list where you have each of these pairs describes an edge. You've got source and target vertex. And they're just, just all of the edges are listed there. Okay. Here's another style of representation, adjacency list. For every vertex, we list its neighbors in the graph. Okay. And then last but not least, we've got an adjacency matrix structure here, where you basically have like a Boolean, like yes or no. The check marks here are yes. There's an edge between like Boulder and Vale, means there's a road directly between those two. Okay. These are sort of some of the most classical representations. Out in the wild, we see even more representations, very application-specific structures where you just have random pointers, sort of that you can think about as being a graph structure. And then we have lots of graph algorithms. It's actually amazing how many different things out there you can think of as graph algorithms. And I have a feeling that a lot of people accidentally re-implement graph algorithms all the time. And so I think the BGL probably could get used a lot more if people just realize that what they're working on happens to be a graph algorithm. But that's sort of this, it takes a little bit of mathematical training to realize when a particular abstraction, to recognize that it's useful in a particular place. So here's one problem. How do you find your way out of a maze? By the way, who knows the difference between a maze and a labyrinth?
There's a way out.
Islands.
There's a way out. That's almost right. A labyrinth, there's only one path. So it's always really easy to find your way to the middle of the labyrinth, because there's really only one path. Whereas a maze is actually tricky. There's dead ends. It may take you a long time to find the right path to the end. Okay, so how do you find your way out of a maze? Well, if you're familiar with graph algorithms, you can just say, hey, that's just depth first search. Okay, or in fact, you could use any exhaustive search to get yourself out of a maze. Okay, and so with depth first search, this is the trick where you mark where you've been. And then if you hit a dead end, you backtrack to some hallway or whatever where there's an outgoing sort of way that you haven't marked yet. Okay. And of course, then you've got all these wonderful stories about like leaving breadcrumbs, but then someone coming behind and eating the breadcrumbs, and you're in trouble. So here's like the pseudocode for your typical depth first search. So you've got a graph G, and you've got some vertex U, which is your starting point. And then you mark that vertex. I'm going to mark it black, so a check mark to say I've been there. Okay. And then you look at all your neighbors, so all the paths from your current spot, and you check to see if it's white. That means has it not been visited yet? And if it is white, then you go ahead and recursively go and search down that direction. If you come back from that, having found what you were looking for, then you can say, oh good, I found what I'm looking for, and keep retreating back. If you haven't, then you just go to the next iteration of this loop, try the next path out that still hasn't been visited. Okay, so I want to sort of turn this into a little bit of a design sort of experiment of, let's say you've found some pseudocode in a math textbook somewhere, or a computer science textbook that sort of solves the problem you need. How do you turn that into a C++ implementation of a generic generic function? And the real question there, almost the only question, is what should the type requirements look like for this kind of algorithm? And or another way to say it is, what capabilities do we need from our inputs to get the job done? Okay, so maybe let's just start sort of brainstorming here. What do you guys think are necessary requirements?
We'll start with the very first line of the code there. You need to be able to recognize when you're at the exit.
Yep.
Or at an exit in the case of of multiple exits.
Right. Yeah, absolutely. And can you think of like what might be a way of, representing that in terms of C++?
It must satisfy some sort of predicate.
Right. And would you have that predicate written out right here? Or
that
would
would be one of mine.
Type parameters for DFS.
that would be one of your inputs? So you input a predicate.
Right.
Exactly. Yep.
And
Right.
the predicate has its own set of requirements. It says given a graph, returns true or false. If,
Or given a vertex. Yeah.
well,
Yeah.
it needs the graph. I think it would need the graph as well.
Possibly. Sure.
Possibly.
Yeah.
Then we need to efficiently mark the vertices.
Right, so how do we do this? This pseudocode is sort of suggestively sort of used brackets, which might make us think about arrays, but would it be okay to just say, okay, fine, we're just going to internally use an array? Does that make sense? What do you guys think? Should we use an array? Thomas is saying no. Anyone else have an opinion?
You have no idea how big the graph is, so that doesn't sound like a good idea.
Okay, so you're worried about space consumption?
Well,
Well,
yeah.
and
reallocation.
How are we going to look into the arrays then?
How do you
because
look-
We need to translate the vertex to the index of the array.
Right. So how do you go from a vertex to an integer offset, right? Which would be how you'd access an array. There are a lot of graph representations where you do have integers sitting around for every vertex, but there also are plenty of other graph representations where you don't have integers. For example, consider sort of your typical graph as giant pointer structure in memory, right? There aren't any integers sitting around for every node, so this would not work for that. Hey, Dean?
I would make mark an actual operation instead of so I can make it a little more permissive. I just say, okay, mark you the vertex as being black at this time.
Yeah.
So how mark is implemented would be
Hidden.
hidden.
That's right. That's a great idea. And we have to just flesh that out a little bit more. So we need to be able to associate black with you, and then later on we need to be able to read it back out. Right? This is a read operation here, and compare it to white. Okay, and that's basically it. We need to be able to read and write to this thing. Okay, and that's it.
So
So
what thing? Because you're not necessarily going to read and write to you. You just need to
you
associate.
need an
something with a specific
association.
instance.
This is actually a relationship. You want to have a relationship between you and color and this coloring, black or white. Right? So we need some way of talking about relationships.
Or
Okay.
some generic property.
That's right. After we do this brainstorming session, we'll show sort of what I came up with for all of this.
Obviously you need to get the adjacency.
Right, so we need to be able to ask for what are the adjacent vertices.
And then that in itself presents a problem of how do you return those?
Sure. Yeah, how do you you could be naive about it. In fact, there's like old versions of like Leda. They're my competitor. But their new versions are better. But the old version, like, you return like a list by value out of this thing. It's just mind-bogglingly bad for performance reasons. But yeah, you want to be smart about how you do that. I think that might be it.
Don't you have to give mark back in that recursive DFS call? Because you lose it now.
I'm sorry, what was that?
The mark array or map, or how do you call it, has to be returned in that recursive call DFS.
Yes. Yes. This is pseudocode, and it's sort of not necessarily.
Oh, okay.
But maybe mark really should have been a parameter here.
Yeah, I think so.
Yeah, absolutely right. And this is where, like, a lot of times you're looking at pseudocode in some textbook, and it may, assume some things are global. And oftentimes when you're dealing with libraries, global is like, you never want to do that, right? Okay, so what we've just come up with are all of these requirements here, right? These are all these needs that the algorithm has. Okay. So what I did when I was coming up with the Boost Graph library is I basically just sort of looked at those needs and then invented concepts to match each one. So this this is the adjacency graph concept, and what it does is it says, it provides a function, or this is the valid expression for this concept, where you can ask for the adjacent vertices of a particular vertex in a particular graph. Okay? And what you get back is a pair of this thing called an adjacency iterator. And in the adjacency iterator, it's a first-last pair. So you can iterate through that range to get all of the adjacent vertices. Furthermore, there's some associated types. If you've got an adjacency graph, you can ask, what is the vertex descriptor? The term descriptor is a little bit funny, but all this is a handle for a vertex. Now that handle, the type of that handle could actually depend on the graph that you're dealing with. It might be an integer, it might be a pointer, who knows what. The algorithm doesn't care what it is as long as it sort of plays the right role. Okay? Question?
So why specify that it returns a pair of adjacency iterators and not specify that it returns a range?
A pair is a range.
Yeah,
Yeah.
but a range might not be a pair.
But a pair sort of does enough. Well, actually, what do you mean by a range, actually?
And this precedes range by.
Yeah.
So this does precede range, but thankfully, when they built range, they made sure that pairs of iterators would be ranges.
But you might want to have your own graph structure that would have something else that is not a pair and return that immediately instead of making a pair.
Yes, but it's actually, the choice of pair is sort of minimally intrusive, that you could go ahead and wrap your let's say you have your own graph data structure.
I mean, in the pseudocode you wrote, the last part is basically std find with where you're searching for a node in the adjacent vertices that hasn't yet been marked, and that satisfies the condition.
Okay, well, that's not quite right, but I mean, getting back to your question about, like, let's say you have some new graph class, like, would it be sort of onerous to implement this? The answer is no. I mean, if you have a range, any kind of range object, then it's trivial to create a pair of iterators, right? So this really is sort of a minimalistic requirement on things, and thankfully, like, once, you know, range algorithms and these kind of things come along, this stuff just works, right? So.
But by saying that, aren't you advocating that every sort of concept specification should be replaced by something that is minimally obtrusive and can satisfy that concept?
Yes.
But then why would you use a concept at all?
Because so this is this trade-off between what the algorithm needs and what data structures can provide. And so that's why the algorithm writer always wants to minimize his requirements, but he can only go so far. Like, I have to somehow have a way of accessing or asking for the adjacent vertices.
You have to be able to iterate them, but do you have to know that? Do you have to get a pair of iterators?
So there's only, what I would say is that there's only a syntactic difference between this and any other thing that you'd care about, and so these syntactic differences are very easy to sort of gloss over and fix. Okay. What's important is there are no semantic sort of requirements here that sort of that some data structure is incapable of like adding glue code and making it work. And so this sort of from the, you know, maybe I should say yes, like if I were going to do this over again, and now that there's the range interfaces, that would be a way of loosening the specification up a little bit, and that'd be a small improvement. So I think that's probably the easiest thing to say about that. Okay. But yeah,
Sorry. Just to follow that discussion, for example, I was working on a graph that I didn't know the extent of in the beginning.
Sure.
So then how would I do this if it was a pair of iterators when I don't know the extent?
It's not the, well, here you just need, this just says that if you're at a particular, if you're at one vertex here, you need to know who you're connected to, and that's it.
Okay.
That's all it's saying. That's all this is just the neighboring guys. And
Right,
if
so-
you don't know the neighboring guys, then you really can't run this algorithm.
So then, why can't I just give you a handle to something that you can iterate?
That's what this is. That's what this is.
You would abstract that in the iterator itself.
So this adjacency iterator, maybe I should take a step back here. This is not a class. This adjacency iterator here, it's an associated type,
Right.
which means that for any particular graph implementation, you get to pick whatever you want.
Okay. All right.
So there's a game here.
So then
You
I
get
have
to pick.
Yeah. So I then have to make it an iterator first, so that
Well, you need to when you
Yeah,
implement your adjacency iterator for your class, you need to provide.
It's a concept, isn't it?
You've got
It must
follow-
model multi-pass input iterator.
all right.
Okay.
Okay.
So you got to do that, or else the code won't work. Right?
Okay.
Because you need to. So that means you need to provide like dereference and plus plus and like I equal to j. Right? You did those are the main ones. Now, actually, here's an interesting question. Why? So this multi-pass input iterator, you probably haven't heard of that, right? So, and I'll tell you a little bit about that. That, let's call it MP iter. It comes in between forward and input. Okay? And the reason why it exists is because two things. There's requirements in here in forward iterator that aren't needed by a lot of these graph algorithms. Okay? In particular, requiring that when you do a dereference that you get an actual L value reference back. That's not really a requirement of a lot of these algorithms. The other side of that is that there's some graph data structures where you can't give back an L value. Okay, so for example, a little bit later on, I'll talk about a Knight's Tour graph where the graph doesn't really exist.
Yeah.
Okay, and if it doesn't exist, you can't give an L value to it. Okay, so there's specific examples that say why we need this guy in between, and this is part of the motivation for why we came up with new iterator concept hierarchy. All right.
So, can you say that the adjacency iterator is a concept that inherits from multi-pass iterator concept?
No. So
That's the association.
adjacent. So these are associated types, right? So anything that wants to model adjacency graph has to provide an adjacency iterator. Okay, and you do that using by type defs and traits and stuff like that. But you have to go and implement some guy.
But that's
And
about
then
the
that-
requirements.
That adjacency iterator has to implement multi-pass input iterator.
Well, fundamentally, from your requirement standpoint, they're all concepts. Because they're just a bunch of requirements from whatever the adjacency, the iterator type def is. It has to support,
Well, I wouldn't say that adjacency iterator is a concept. Okay, I would say that it's an associated type that is part of the requirement of this concept, and then we then put other requirements on that associated type, which are expressed by another concept. So it's certainly, associated types are part of what makes up a concept, and you can use concepts to constrain them, but I wouldn't say that an associated type is a concept. It's always just part of
So, if you have a vertex, and then you take your adjacency iterator, how far does it go? Just to its adjacent one, or can you go further down the
just the adjacent ones.
Just the adjacent, you can't go down the.
You have to,
adjacent ones beyond
once
that.
you get an adjacent guy, you can then take this vertex and say, what are your adjacent? You can get an adjacency iterator for this guy.
Oh, you have to keep that in your iterator.
Yeah, and that's actually what happens in the code here.
That's why it was re-entering.
Yeah, that's why it's recursive. So if we go back to the pseudocode, we get this V is sort of the result of dereferencing the adjacency iterator, and then you then do a recursive call, which then asks for its adjacency. So, all right. Okay, how about marking? This is where the property map concepts come into play. And this is a really simple set of concepts. We have one that lets you do reading. So you can say get with the property map and a key that gives you back a reference to the value underneath. and then put, where you can give it a key value pair, and it'll associate the key and value together.
I was always wondering what was the complexity of the property map, because it's nowhere stated in the Boost
Ah, my bad. It's supposed to be constant time or amortized. Usually when we say constant time, we mean amortized constant time. Now, we often use red-black trees, for example, in here, and so then you're getting logarithmic time. So.
Yeah, you've just reinforced the thing we started at the beginning of the.
Sometimes we lie.
We lie.
Yeah. Yeah, but maybe more commonly you'll see, at least maybe one of the way to say it is if you're lying, know that you're lying and know that what guarantees are no longer hold.
Yeah.
Or what if you just give an upper bound and say
That's what what those guarantees are. They are upper bounds,
That is what
and the upper bounds are no longer valid.
right? So when you say you just make it, at most exponential.
No, but you can't do that. Like let's say get is not. Let's say this you call get and then it's not exponential time. It's bigger somehow. Let's not get into the weeds here. we could discuss this
I have
further.
a very quick question. Is reference in that case an associated type, or is it an actual T reference?
Convertible.
No, is that?
So it's an associated type.
Oh.
It's associated type right here.
Sorry.
And I'm going fast, but it is.
Yeah, thank you.
So this is pretty darn loose right here, and it's meant to be that way. And then we need a way to carry out custom actions during the search, like checking for success and terminating and things like that. I think I'm gonna skip over this part. What I'm kind of skipping over is that just this white-black marking is sort of coarse, and you can actually there's a lot of information you might miss out on if you only do white and black marking. For example, you might want to catch that there's a cycle, like this guy has a cycle back going to here. And it'd be nice to realize when you have cycles. Let's say you're trying to build like a makefile tool or something, you wanted to see if there's cycles in your file dependencies or something. And if you add a gray color to your color scheme, then you can, and if you're going along and you see something that's gray, then you can tell that, oh, now I've got a cycle. And you can't really see it. These are gray here, this guy's black. This blue edge here is saying, oh, I'm a black guy, and I'm looking and I see a gray guy. That means he was one of my ancestors in the tree, and so I've got a back edge. So once we have this new color scheme, we can sort of put in a whole bunch of generic callbacks into the depth first search algorithm. When you first initialize a vertex, when you discover a vertex for the first time, when you're looking at an edge, when you've figured out, oh, this is a tree edge, this is an edge that I'd actually traverse to find where I need to go. A back edge, right, this is where you've got a cycle, or where you've got a forward or cross edge. And so what the idea here with this DFS visitor is it's this basically, it's a lot like, you're used to a lot of STL functions where you pass in a functor as sort of like a callback. This is like a whole bunch of callbacks sort of glommed together, and you pass them in as one big class that sort of, and I've done a little bit of work to make this easy where, there's sort of like a default guy that doesn't do anything, and you just override the ones that you actually want to implement. And so that makes it sort of easy to sort of plug in which callbacks you want.
Are visitors allowed to modify their arguments?
No. In general, no. You could.
Just more like tourists, basically.
Yeah. So if you were to start modifying the vertex or the graph, like if you were to start like changing the graph structure, then the iteration would very easily get screwed up.
Like marking, for instance.
No, the marking, that's not changing the graph structure, and that's going through the property map interface. And so yeah, yeah, you're definitely going to be changing marks and stuff like that. Or you might even have other property maps that you want to keep track of in your visitor. Like that's how we implement the shortest paths.
And the property map, is it directly associated with the graph instance, or is it kept separately?
This, it's just, it's set, well, yes and no.
Yeah.
Okay, so that's the, in some sense, that's sort of the wrong question. And it's a natural question to ask, but because of the generic programming style here, what we've done is we've said that you pass something called something that implements the property map interface into the algorithm. Okay? Now, this interface is so generic that it might so happen that the actual data is sitting on a struct with the node. Okay? And you could implement this get and put could just be like doing field member, data member access. Or it could be that you've got this hash table off to the side. And this get and put are going into that hash table and accessing it. So because of this highly generic interface, you can deal with whatever you throw at it can handle, no problem. So.
Because I was just curious because that addresses the question. If it's separate, then the visitor is not modifying the actual graph in a sense. But because if you have two visitors, doing their job, then they're gonna.
Right. So the key thing is that you're not changing the graph structure, the adjacency structure.
At this level, you don't care if it's
right.
Okay.
One more concept. One thing you'll notice that when we started talking about this DFS visitor, we started talking about edges, not just vertices. And so now, instead of just talking, like let's say this is our current vertex here, instead of just saying who's adjacent to me, you also want to talk about the edges. So what this concept here, on the next slide, this incidence graph concept, this gives you access to the edges that are what's called incident to the current vertex. Okay? So you can ask for the out edges, you can ask for the source and the target. Now there's a couple other concepts that I won't show you, but there's ones that allow you to access the in edges, and also there's versions that are undirected. But for search, this is what we need, is just be able to access the out edges. And then once you have an edge, and notice that I haven't hard-coded what an edge has to be. There's just this associated type edge descriptor. And if you're implementing a graph, you need to provide some type that provides a source and target function. And sort of is the thing that you get when you dereference an out edge iterator. So this is what the depth first visit function looks like in the Boost Graph library. Now the graph is parameterized, and it needs to be a model of incidence graph. You need to pass in where you're starting your search, and that thing has to be of the vertex descriptor for that graph. And of course, we use trace to map that across. And then you have to pass in a property map, and then a visitor to tell it what you want to do during the search.
When you say it's looking like this in the graph library, it's looking like this, or it's looking with a small line with a boost concept checked between the first two?
Well, so here I put the semicolon. This is just the.
No, between template and.
Oh, you mean here?
Yes.
Well, you mean like once we have concepts in the language someday?
Because you wrote a concept library, right?
Oh, you mean the concept checking library? Yeah. So yeah, concept checks are in here. The library version is already in here. Yeah. And depending, when I put them in, it was a bunch of in the first few lines of the implementations where those show up. There may be a newer version that uses macros to put them up here instead.
Because you don't have any no OX for this, I was wondering how you implement it.
Yeah, it would take another whole talk to tell you how I implemented the concept checking library.
No, not the concept check. If you implement it or if you waited for the OX to come.
Well, no, I implemented. I created the concept checking library and then used it on this library.
Okay.
Used it here. Yeah. I mean, that was a lot of the motivation, like after having created the concept tracking library and using it on the Boost Graph library, you know, I was like, oh, this is frustrating, like it doesn't quite get the job done. And that sort of motivated the work on the language feature. So here's a, let's think about applications, right? How do you, so I've shown you all this generic stuff. You know, now, what if we're actually trying to solve a particular problem? What if we want to find a path that gets us out of the maze, right? And by a path, I mean, you know, a list of some kind of something that we can sort of recover. You know, the list of edges, list of vertices, something that sort of tells us, you know, because the depth first search will actually explore the entire graph. But how do we get the path to the way out? And how would we use, you know, just making a call to this function here to get that job done?
Do you want any path or the shortest path?
Well, let's just say that there was something here that was the exit. So, I mean, if you want to do some post-processing, that's fine too. But the key thing is that there was some exit somewhere, and you want to keep that path.
I think we should know a little bit more about visitor if visitor is able to interrupt visitation.
Yeah. So that's a good question. Maybe I'll say a little bit more about this visitor. So it's, in some sense, all of, by interrupt you mean stop the algorithm. So that's an interesting question. We've sort of gone back and forth on that. The kind of the answer to that I've sort of historically pushed is that there's this feature called exceptions that's been talked about in the other world. And those are a great way to short-circuit it.
Every C++ book states you shouldn't use exception just to signal somehow behavior where you, let's say, should...
Let's take that discussion
not
somewhere
error.
else.
That sounds like a good one for lunch.
So I would suggest, so my answer to that is, so it's good that lots of people say a certain thing. What are the reasons for them saying that, and do those reasons apply to this? And think sort of independently for yourself as to, and also think about the performance implications, think about it all, and check whether, because any global, like you're sort of talking about this global statement, right? And whenever there's a global statement, you know, when it actually comes down to it, on any given instance, it may or may not be true. And so you want to sort of think about the rationale for the global statement and why would it be true or not true in this given instance.
Actually, I would expect here some kind of an interface like find if in STL, because I could pass a predicate.
That's the other. That's the other obvious alternative for how to do it. And so so let's take this offline. But there's good reasons for the exception-based approach. I'll just leave it at that, and that it's not as cut and dry as it might seem. So. I would even go so far to argue that it's better. Okay. So, but that's a whole nother topic. Okay, so how do we solve this problem? How do we keep track of it?
So if you relax the requirement on the return of the adjacent vertices, and you can return anything that is arranged there, you have something on the stack that you control on the side. On your side.
No, you're cheating.
Exactly.
You're not allowed to change. You're not allowed to change anything.
So my final question is,
you're stuck with this. You're stuck with this.
The visitor.
You're stuck with this. You know, you're stuck with. You know.
You can still fiddle with the agency iterator and put something there that will be inside the pair.
Fiddling with the adjacency iterator is allowed because you're the one that's providing you're passing the graph in. But I would say that that's definitely not the most straightforward way to do it.
So just looking at your function signature, are you assuming that the visitor is a stateless object?
No. I mean, it's got to be a stateful visitor, hasn't it?
In some sense, there's got to be some state somewhere. You want to record these paths, right? So there's got to be some state.
It's copied by value.
Yeah, so you have a,
Yeah, so you lose your you lose the changes.
You could
No.
pass it as
So you pass a pointer.
Yeah.
So your visitor has a pointer to an array.
So your visitor keeps a stack of your things when the predicate is satisfied when you do visit the discover vertex. When
Sure.
your predicate is true on that, you throw an exception on there.
Right. So that's a great way to do it. You have a stack when you let's see what you do when you go over a tree edge. You could sort of push the target on.
I wonder when you return failure, you pop it off.
Yeah, when you return failure, you pop it off. That's basically what you need to do. I think there's a missing event here of finish vertex,
Yes.
Yeah, I wondered about
that.
which should be up here. Like I'm positive it's in the actual library. And so finish vertex would be where you'd do the popping and also where you'd be looking at whether you're at the exit or not.
That'll help.
So finish, yeah. I don't know, how did it not get in there? Because it's definitely in the library. Yeah. Right, so that's one way to do it. Another way to do it is not, you could, the stack is probably the best way because it's the most space efficient, but you could just, for the entire depth first tree that's formed by the whole search, you could record, for every tree edge, you could record that edge. Usually by like maybe saying, what's the parent of this guy? So you can work your way backwards. That would be a pretty common way to do it. And then when you finally exit and find your exit, you then could just say, oh, traverse backwards using these parent pointers to reconstruct the path.
Probably
That's
easier.
not always possible if you have multiple paths. Some
No, it is-
will-
No, it is
some will have
possible.
multiple parents.
No, because what comes out of the depth first search is a tree.
Yeah.
These tree edges. Now, by definition, a tree only has one parent per node.
Yeah. Which is fine.
So you always can.
Oh, you build a tree. Okay.
Yeah, what I'm saying is use these parent pointers to always remember. Yeah, so when you hit a tree edge, you say, oh, target vertex, his parent is the source vertex.
We need also to ensure that the graph is
We're
connected.
Right, so to deal with graphs that aren't connected, what you typically do is you don't use depth first visit. There's this other function that goes on top of it called depth first search, which restarts the search by looking through the entire list of vertices, trying to find one that it never got to because it wasn't connected, and restarts the search from there. So
You have a tough time getting out of a maze which you're not connected.
yeah.
Walking off.
Yeah, so so for the maze example, this is sort of a mute point.
All right.
Would you use
Just-
your color?
Just so you know, we are at the end of the tape.
Okay, well, I think probably the thing to do is just, as long as you guys want to keep going, I could go till like 1, if you guys are interested. Okay, cool.
We got,
And we just won't have the whole thing.
right, it's got like 2 minutes left.
Yeah,
Yes, we get slides afterwards
Mhm.
as
Yeah.
well, huh?
yeah,
So then we can proceed.
yeah, absolutely. All right, so here's the actual implementation of depth first visit. A little snazzed up. This isn't the way it looks like in the header file. Like I had to put in the new for loop and stuff like that. So what's going on here? You know, you're marking that a vertex is gray, calling that discover vertex event point. Then we're iterating over the out edges. We've got our target vertex V, checking that whether the color's white or not. You know, here, like, this puts some constraints on the property map and the value, sort of the values that are in the property map. So they really have to be these things that, you know, can be compared to, I think it's this enumerated thing of white, black, or gray. Now here we've got, you're sort of saying, hey, we found a tree edge, and then we're going to go and visit down into recursively visit the rest of the graph down in that part of the graph. After coming back, or another alternative if it's already gray, and we've found the back edge, otherwise it's a forward or cross edge. And then once we're out of this loop, then here is marking it as black, and here's also where the finish vertex call should be. which I somehow left off of that as well. So that's how the C code would actually, or the C++ code would actually look for this. Okay. So that's just a quick sort of taster for what one of those looks like and how it came about. There's, lots more algorithms in there, and there's more being added. And so, think twice before sort of implementing your own graph algorithm. You might be able to save yourself some work, and there might be something already there. And it may take a little bit of thinking. Like, how it wasn't exactly obvious how to solve this problem using depth first search. There's a little bit of thinking there, and a little bit of like, how do I fit into this existing interface? But a lot of times, these things are pretty maximally generic. If anyone, the complaints that I typically hear about the graph library aren't that it's not generic enough. It's usually that it's too generic or too complicated. Okay, so it's pretty rare that you can't actually get the job done.